This is where we finished last time. Well, we had the sort of complete set of equations of motion for the two green functions, gr and ga, and the two what we call correlation functions, gn and gp. And gn is what gives you the electron density, and gp is what gives you the hole density. And I guess these said they're on page 18, so we got up to page 18 of the notes. And I guess what comes next is a few considerations when you're numerically calculating these things, just a way to reformulate the equations which are more numerically efficient. And then in the later chapters we'll get much more deeply into numerical algorithms. But right now, just to sort of set the stage, we'll reformulate these where you just require different parts of the matrix to get the same quantity, like transmission or electron density. So this is just reformulating our equations. Okay, reformulating the equations we have for numerical efficiency. And I guess this is section 1.2.5 of the notes. Okay, so let's see. What do we want to do first? So we had an expression for the transmission that looked like this. Gamma 1,1 G R1N gamma NN and GA N comma 1. This was our expression for the transmission, and you know, when a device is a matrix like this, it means that you need to calculate these, the 1n element of the green function. So that's row 1, row column. Row 1, column n. So this far corner element of the inverse of the green function, right? Can you picture that? You got your matrix, you need this far right-hand upper corner element of the inverse. You have E minus H minus sigma inverse. And there's no real numerically efficient way of getting that. There are numerically efficient ways of getting, as we'll talk about in detail later, if you just want like the 1,1 element of an inverse, or the NN element, a low upper corner or lower corner element of an inverse. That you can get very efficiently, because that would be all you need. I mean, if that is all you need. And so we're going to reformulate that to calculate the transmission, where you only need the 1,1 element of the green function. So when you go to calculate it, you can come up with some very numerically efficient algorithms. Okay, so to do that, we note that this thing here is the right connected spectral function. That was our definition of the right connected spectral function. This is the component of the spectral function that's injected from the right lead. Right? The spectral function has two pieces, one injected from the right lead, so you can think of this as like, right, the psi squared due to injection from the right lead, our right scattering state magnitude squared. And we also had a similar one for the left spectral function where you just would have a gamma 1,1 in there. Right? Everything we inject from both the left and the right, the spectral function is a sum of everything. Okay? But we also know that the full spectral function A11 is just A left 1,1 plus A right 1,1. So I'm going to replace AR up there, AR 1,1, with the full spectral function minus A left. And so when I do that, I have that T is equal to gamma 1,1 times A11 minus A left 1,1. And that's equal to negative gamma 1,1 times 2 imaginary G11 plus GR11 gamma 1,1 GR star. Right, because the full spectral, so you use this relation here, and you also use the fact that the full spectral function A11 is negative 2 imaginary G11. At least if they're all scalars. If they were like block matrices, then you would use it's equal to I times GR11 minus GR11 dagger. But again, you only need the 1,1 block. That's the important point. You only need the 1,1 block of everything if you're dealing with block matrices. And so there's some very efficient algorithms out there to just get the corner block of an inverse and nothing else. There are no really efficient algorithms. Well, okay. It's less efficient if you have to get far off diagonal blocks. So that's one way we can rearrange the equations, using these relationships between the spectral functions and the green functions and the left, and the fact that A is A left plus A right. Okay. So this is the numerically efficient expression for getting the transmission coefficient. But for device modeling, you need not only the transmission coefficient, you also want electron density. And so now let's look at our expression for electron density. So we had that Nj is 2 over A, and that's for spin, the 2, integral dE over 2 pi. And then we wrote it out as G gamma, but this is really just A left, JJ, times f of e minus mu left plus a right jj times f of e minus mu right and this is our in the notes. I've just written it more compactly. A left, now this is the way we think about it. A left times F left plus A right times F right. That's what gives you your charge density. And we use the same trick that we just used. So let me, A left, to make it clear why we're doing this, is GR J1 gamma 11 GA 1J, right? That's our A left. And we're going to write, again, we're going to make the same substitution we did last time. For A right, we're going to write that as a full spectral function, A minus A left and so we're going to, and then, so if you do that, you're going to have two terms with an A left in it. You got an A left here. You still have your A left over there. So they're going to combine, and you got the minus sign. So they're going to combine, and we finally have NJ is 2 over A integral dE over 2 pi times GRJ1 gamma 11 GA1J times F left minus F right. That's combining the two A left terms. And that's where that negative sign comes in. Right, because A left in red was multiplied by F right. But it has a negative sign in front of it. And we got the term left over due to the full spectral function, which I'll write as, again, negative 2 imaginary g. So negative 2 imaginary g times F right. So this is about getting the electron density is a little harder than getting the transmission. For the transmission, we showed all we need is a 1-1 block of the green function. Right? To get the transmission, we just need the 1-1 block of the green function. That's all we need. To get the electron density is not quite so easy, but this is the simplest expression we can come up with. So to get the electron density, you need the diagonal elements of the green function. All of them across your whole device. You need the diagonal elements of the inverse. If you think of the green function as the inverse of E minus H minus sigma, which is what you would do in MATLAB, you need the diagonal elements of that inverse. And this is why I'm going through this and we spend so much time, because taking the inverse of a matrix is really a numerically inefficient thing to do. If you can get by with just grabbing the elements you need of the inverse and not calculate the whole thing, that's a big numerical advantage when these matrices start getting big. And over here, we need the row column. We need the first column of the inverse. So this is, later we'll show some numeric, basically a recursive green function algorithm that will allow you to get these elements and only these elements very efficiently. So allow you to just get the diagonal elements of the inverse and just get that first column and not get anything else, because that's all you need, so you don't waste time generating a bunch of other elements. But right now I'm just showing you how to manipulate the equations into this form. Later we'll show how to actually, you know, the algorithms you need to actually calculate these elements and only these elements. Okay, so that's as far as we're going to go for the moment, and now I'm going to back up a little bit and just start this, what's called this standard discussion in the notes. This is a discussion you see in textbooks when they, standard discussion for green functions, something more similar to what you may have already seen in the quantum mechanics class. Sort of tie the two points of view together, because, you know, we've derived this expression for our retarded green function, but it looks like nothing you've ever seen before from your quantum mechanics class, where you probably in scattering theory you may have run across the green function, but you know, it doesn't look like what we've done at all here in terms of formally the way we derived this and it came about. So let's start with the usually the way it's started off in a standard quantum mechanics course. We start off with the time-dependent Schrodinger equation, h bar d dt psi. And so the formal solution is psi of t is equal to e to the minus I Hamiltonian t minus t prime, or that's your full Hamiltonian operator, over h bar times the wave function at time t prime. Right, that's the formal solution, where h is your Hamiltonian operator. And psi of t prime would be your initial condition, right? This is essentially your initial condition. Generally, you take t equal to 0, for example. And this equation is valid for all t, for both t greater than t prime and t less than t prime. And in the domain for t greater than t prime, that's called the causal response. So for t greater than t prime, that's going to be the causal response of the system. So it's, you know, the response to some initial condition as the time increases. So we can write this causal response as e to the minus I h of t minus t prime over h bar times your unit step function. Right, that's our causal response of the system, where theta t is your usual, you know, step function. For t greater than t prime, it's 1. For t less than t prime, it's 0. Right, your usual step function. And then, in the time domain, we can define our green function in the time domain, since this is a causal response, and we've been talking about our causal green function, this retarded green function. gr of t minus t prime is equal to minus I over h bar times this exponential e to the minus I h t minus t prime over h bar times its step function. And so the units of this, what are the units of this green function? What are the units of this green function? It's always good to be aware of units.
seconds.
That's right. Units of 1 over h bar, which is 1 over energy seconds. All right. What were the units of our green function that we had before, previously? 1 over energy. So because this is in the time domain, we're going to see how this comes about in a moment. We have 1 over energy seconds. But remember, one is a Fourier transform of the other, so that when we Fourier transform, that seconds is going to disappear and we'll get energy. But for the moment, let's just see why this is the green function. So if we, we show that this is the green function by showing that it satisfies the equation IH bar ddt minus h acting on g is equal to delta. I mean, if it satisfies that equation, then that is by definition a green function. That is the impulse response of the system. And so then you just go ahead and you work it out. So we have what do we got? We're going to have two terms. Let me copy and paste that over. Okay, so let's see. If we work on the derivative term, right, the ddt term, and so this is our g is our e to the minus I h t minus t prime over h bar times theta. And so now IH bar ddt times, we'll just look at IH bar ddt times this. Just take the derivative of that. And so I guess when I let it first act on, there's two terms, we got to use the product rule, right? So I'm going to have a IH bar, and when I take the derivative, it's going to pull down my minus I times big H over h bar, right? And I'll get my exponential back. I'll get everything back again. I'll get my green function back. Plus, letting it act on the theta term, I'm just going to get IH bar. I guess I'm going to, what am I going to get? I'm just going to get, okay, I'm factoring out the IH bar. Let me get rid of that. I'm just going to get delta, right? Delta t minus t prime. Letting it act on the theta term, and then I get my green function back. Is that right? No, I don't get my green function back. I get I'm trying to go too fast. Okay. So term by term, I'm going to get this is going to be multiplied by my green function. And I just pulled that out of the exponential, nothing else. I get my exponential back. And then this term is going to be multiplied, well, I killed off my theta, right? So I'm just going to have the exponential left because over h bar, because I killed off my theta term and turned it into a delta function. And now, oh, and I got another factor too, right? My green function was defined with a minus IH bar out front. The green function has another minus IH bar out front. So I've got the whole thing times a minus I over h bar. That was the definition of our green function. Okay, so let's see what happens. What's going to be left? So I'm going to have the I and the minus I kills each other off, the h bar, so I'm going to have an h acting on the g, right? This term is going to give me an h acting on the g. This is going to give me this term here, h acting on g. this term here, well, it's only non-zero when t equals t prime. So I can evaluate this when t equals t prime, since that's the only time that matters. And if I evaluate that when that equals t prime, that just gives me 1. Okay? So this gives me an h of gr plus delta t minus t prime. And then I have this term out here, right, a minus h. So finally I subtract off a minus h gr from that term, which cancels. And so indeed, this does satisfy your equation of motion in the time domain. This would be the equivalent of our equation of motion. Remember, in the energy domain, we had E minus HD minus sigma G equals the identity matrix. In the time domain, the identity matrix is basically your delta T minus T prime. So we've showed that this does satisfy the equation of motion for the retarded Green function in the time domain, which is this guy up here. So this does indeed, the way we've defined it, satisfy the equation of motion. We'll see when we Fourier transform it, we're going to get something that looks like our retarded Green function that we had in the energy domain. And we'll Fourier transform the t minus t prime coordinate to go from time to energy. Fourier transform the time difference. So I guess that's it. So I guess I will see you next Friday.
For the chemical potentials on the last part you're going over,
Yeah.
How do you know those?
They're given by those are the chemical potentials of the contacts. So you know the doping of your contacts. And if you know the doping, then you know where the Fermi levels are. And you know if there is an applied bias, then they're going to be split by the applied bias.